Let's try example 6. So I have all of the data points already input into list 1. So I would say pause here to input those into your calculator if you'd like to follow along. Okay, what we're going to do is construct a 95% and a 90% confidence interval, and we're going to compare them. Now, as we said before, when we go through and we use this, we need to know what our sample standard deviation is. So I'm going to run a one variable stat test on this list. Okay, and we're looking at our sample standard deviation. So you can see here where the S is for sample, our sample standard deviation is equal to 5.752. So that's the number that I'm going to use when we go through now to find our Z interval for either confidence level. So we're going to hit the stat button, scroll over to calc, scroll over to tests, and I'm hitting number 7, which is Z interval. So I've selected data. We're now going to clear out the old standard deviation that was there. And I'm going to put my new one. Okay. Let's start with the 90% confidence interval. And let's scroll down and hit calculate. So here are my numbers, and I'm going to write these down. I have 10.806, 806. Okay. And then I'm just going to draw like kind of like a quick little number line here. And then we're looking at 14.261. Between those two, that would be my 90%. What I'm going to do now is go back into that Z interval. And instead of it being a 90% confidence interval, I'm going to change this to say 95. And we're going to see what happens. So now we have 10.475, excuse me, which let's say is right around here. And then we're going to 14.592, we'll say is over here. So you can see here when we increased our confidence level, the numbers got further apart because we are going through, and by creating a larger confidence interval, we're creating more space or more opportunity for the mean to fall within those two values. So the larger the confidence interval, the more confident we are, or I should say, the more confident we are, the larger the confidence interval. Okay. So we've gone through and seen how we're able to calculate these intervals. Now, what happens if we know what we want to be within, but we don't know how many people or how many items to survey? Okay. I want to remind you, and I'm going to put this as a full screen for right now. Okay. The maximum error that we can have, so what we add and subtract to our sample mean, you're taking your Z-score based on how confident you are, that's your critical value, multiplying by your standard deviation divided by the squared of n. Okay, so that formula we've been using. If we were to solve this formula for n, go through and do some algebra, we're going to get that the sample size we need, we're going to take the critical value times the standard deviation divided by the error that we want to be within, and we square it. That's going to get us what our sample size should be, or the sample size needed to be within a certain amount. So let's use this in the context of a problem. Okay. How large a sample is necessary? College president asks the stat teacher to estimate the average age of students at their college. The estimate should be accurate within 1 year. Whatever you want to be within, that is your error. Previous standard deviation age is known to be 3 years. Okay, so there's your standard deviation. 95% confident, if you recall back to the previous couple pages, 95% confident, that critical value is 1.96. So I'm going to go back down here. It's 1.96. So I'm going to list out all of my values. We have the error is 1. My standard deviation is 3. And that critical value is 1.96. So I'm going to copy down the formula. You have your critical value times your standard deviation divided by your error squared. And I'm going to plug in everything that I have. So we have 1.96 times 3 divided by 1 squared. Simplifying this and plugging it into my calculator, we get that n is equal to 34.57. Now, this is referring to people, right? We can't survey 57 hundredths of a person. So you always want to round up. It's better to have a larger sample than a smaller sample. Even if your decimal is not one where you would traditionally round up, you need to round up. Always. Okay? So let's try part 2. Okay? So now we want to say 95% confident within 1.5 years. So the only thing that I'm going to change here is what that error is. So let's make that 1.5. Everything else is going to remain the same. Same standard deviation, same confidence level. Okay, so now I'm going to plug in those numbers. So we still have 1.96 times 3 in my numerator, but now my denominator becomes 1.5. Okay, when we multiply that, we get that my sample size is equal to 15.37. Okay, meaning we need at least a size of 16. Okay, now just as a reminder, if you want to be able to use the z-interval, your sample size has to be greater than or equal to 30. So we'll talk about what it means when you have a smaller sample like this. But for the context of this problem, you would just need a sample above 16. Okay, let's do a few more examples. So let's look at the back. Okay. I'm going to go through and do some similar stuff here. So we're looking at how many days must be included. So we're looking for my sample size. That's my goal. So we want to go through and identify those same 3 values. So my error, my standard deviation, and my critical value based on how confident I want to be. You want to estimate the number of rainy days in Ephrata. Standard deviation is 5. 80% confident and within 1 day. So my error is going to be 1. Going back up to that chart for my critical value, 80% confident is going to be looking at 1.28 for that critical value. So let's go back down. Okay, so 1.28. Now I hate to disappoint you. There's not a button in your calculator that can do this particular function. So this is one that you will have to use the formula for and simplify on your own. Okay, so let's go through the process. I'm going to take my critical value, 1.28. Standard deviation is 5. Error is 1. Square it. Okay. Breaking that down and multiplying, I get 40.96 days, which, remember, you always want to round up. So we'd be needing 41 days as my sample size at minimum. You could always get more than that, but that's the minimum that we would need. Now, we took a look at what happens when you change the error, but keep everything else the same, okay? When you change the error of what you want to be within, if you make your error bigger, you don't need as many people. What happens if we make our confidence interval larger? Okay, so I'm going to keep everything the same, but let's see what happens here. So we have our error. Okay, that's still 1. My standard deviation is still 5. But now my critical value, we're talking about being 90% confident. If you flip back to that table, you'll see my critical value for 90% is 1.645. So let's go through and figure it out. What happens when we change that one value? So 1.645. So we're making the number larger. what happens to my sample size needed? Okay. Here I get 67.65, which means that we are rounding up to 68. Okay. And that would be 68 days needed. So we can see here that when you want to be more confident, that means you need a larger sample size. Okay. Always, always. It follows for any time. Okay. All right, we have 2 more problems to do. Let's give it a shot. If you want to pause here and try them yourself and then come back and check, go ahead. I'm going to scroll down now. A soccer ball manufacturer wants to estimate the mean circumference of soccer balls within 0.1 inches. Whatever you want to be within is your error. Okay, so I'm going to jot that down. 0.1. We need standard deviation, and we need our critical value. So standard deviation, 0.25 inches. 99% confident. Now, this is a new one. We haven't used this one yet, but that critical value is 2.58. You can see that in your chart. I'm going to go through, multiply everything out. All right. Multiplying through, I get 41.6, which really means 42 soccer balls needed. All right, let's see what happens when you change the standard deviation. So I'm going to keep everything else the same. So my error stays the same at 0.1. Standard deviation now increases to 0.3 inches instead of 0.25. And I'm still keeping my same critical value at 2.58. So 2.58 times 0.3 this time, divided by 0.1 squared. Going through and multiplying it all out, we get 59.9. And for sake of space, I'm just going to draw an arrow here. Okay. We would need 60 soccer balls for that one. All right, pause here. We are now done with the notes. Go ahead and give your homework a try.